Hey everyone. So welcome back to this deep learning series. And this lecture is going to be on the basics of deep learning. So let's dive right in. Now, the idea of this lecture is to give you a basic understanding of deep learning. We won't be doing a lot of any coding in this lecture, but the idea is before we get started actually building deep learning models, which will be from the next session on, I feel it's important that you understand the big picture of what a neural network is, what the key terminology is. And then when we start building, you'll understand where we're heading, right? So hopefully you enjoy this lecture. Let's go. Now, as the name suggests, neural network is modeled on the human brain, right? So the human brain is made up of neurons, right? Neurons have a body which contains a nucleus. There are dendrites, which is how a neuron connects to another neuron, and an axon. So the axon connects to the other neuron, and the dendrite is where a connection is received. Now, multiple neurons you see here connecting to each other. The connection happens at a synapse or synapse, right? Depending on how you want to pronounce it. And neurons connect based on electrical impulses. So, depending on the action that a human being wants to perform, these neurons in the brain fire and electrical impulses are generated. And this is how the brain works. Now, the brain consists of billions of neurons, right? And so, obviously, researchers figured if we want to try and replicate an intelligence, artificial intelligence, well, what if we create these small, tiny functions and then connect them, right? Like you see in the brain. And maybe we can create something that's quite intelligent, right? So, rather than trying to build this really complex, big mathematical model, they figured maybe this is not a bad idea. And that's what deep learning and neural networks are all about. Okay, so we talked about a neuron. Well, what's the counterpart here? So we have an artificial neuron. So what it has is a function here, right? You have inputs coming in and you have an output that is generated by the neuron. So it's extremely simple, right? It's a very simple kind of model. Now, what does this look like, right? Typically. So what you do is let's break this down. So we have shown you this model in the previous picture. So what happens first is, and in this case, we are saying it's got three inputs, but it could have as many inputs as you want, right? It depends on the problem. If you're taking in an image, maybe every pixel of the image is an input. And so it could have hundreds or maybe even thousands of inputs. If it's, text, you would vectorize it and it could be the size of the vector. So say 512, right? Inputs. In this case, for simplicity, we've got three inputs. And the first thing that happens typically in a neuron is once the inputs are brought in, they are aggregated or combined together. And how that's done is the neuron or the node, and I'll use that word interchangeably, has a set of parameters called weights, right? So it's three inputs. So we've got three weights to this neuron. So it's W1, W2, and W3, which multiply the input X, right? And then a bias is added to that, right? And so that's kind of what happens first. And that gives you an aggregated value X. Once you get the aggregated value X, that's then passed into the second part, which is a function called an activation function. So the activation function basically is, as the name suggests, what decides what comes out of the neuron, right? It decides if the neuron is active. So you could have an activation function which returns an output of zero, and so the neuron is actually inactive, right? Nothing's generated. On the other hand, you could have it generate different values, and these values that are generated by the activation function, and we're calling it Y now, is then passed on. So if it's the last neuron in the network, it's the output. If it's in between, then this then gets passed to the neurons in the next layer. So let's look at an example of this. So you have this function, and we're going to use an activation function called the ReLU function. Now, we'll look at the ReLU function in more detail in subsequent sessions. So don't worry about it. But the basic idea of a ReLU function is that it takes an input X, and if X is less than zero, then the ReLU function returns zero. And if the X is equal to or greater than zero, then the ReLU function returns X, right? And so this is kind of what it looks like, right? You have the input here, and you have the ReLU function. Now here there is a small typo. There is an equal to, right? Okay. So let's give it an initial set of weights. We're just defining these, right? So we've got W1 is 1, W2 is 2, W3 is 0.5, and the B value is 4. I'm just defining this. There's no training or learning or anything happening. I'm just defining this. Let's create an arbitrary set of inputs. So we've got X1 is 1, X2 is 3, and X3 is -2. So what happens? First, it goes into this first piece where it's aggregated. So X is W1 X1 plus W2 X2 plus W3 X3 plus B, which is 1 times 1 plus 2 times 3 or 3 times 2 plus -2 times 0.5 plus 4. You can do the basic maths. This is 1, 3 times 2 is 6, 0.5 times -2 is -1 plus 4, and you get 10. So this value is now 10. What happens next? It goes into the ReLU function. So the ReLU function we've already looked at. This value is greater than 0, so it returns that value itself. So the output of this neuron is 10. So hopefully that's clear, right? And this is one node or one neuron in a neural network. But you see how the inputs come in, they're aggregated, passed on to an activation function. Now, if this value had been less than 0, the ReLU function would have returned 0. So that's quite simple. Now, the next step is you've got this one neuron, as we have seen. How do you connect these neurons? Well, this is one way you could try it out, but luckily, it's not as complicated. There are much better ways of building it. And so this is what a typical deep learning model or a neural network looks like, right? Now, the first layer, so it's organized into layers, right? Where each layer has an ordered set of neurons and nodes. And how it works is the data or the output from one layer goes into the next layer. And then the output from that goes into the next layer, and so on. Now, in this case, we are showing you what is called a fully connected neural network. So every output or the output from each node in a particular layer goes to every node in the next layer. So in this case, you have 3 nodes. So the output from here goes to this neuron, it goes to this neuron, it goes to this node, it goes to this node, and it goes to this node. It goes to all 5 nodes in the next layer. Similarly, the output of this node goes to all 5 nodes, and so on. The same thing happens here. There are architectures where this does not necessarily have to be. There are also scenarios, like a recurrent neural network, where you could have an output from here coming back in. But we'll see that in future sessions. Let's not worry about that. So this is a fully connected neural network, feed-forward neural network, because all the information is going forward. Now, you have an input layer in a neural network, and the input layer is basically the inputs, right? So the inputs, it does nothing else. It's just the input being sent to the next layer. And then you have a function, right? You have inputs, you need an output. So you also have what is called an output layer. And the output layer is the layer that returns the final output of the neural network, which is just a mathematical model or a function, right? Effectively. So you've got the input layer and the output layer, while you have layers in between. They're called the hidden layers, right? In this case, you see there are 3 hidden layers, right? And so that is where a lot of the computation happens. You see what the output of the network, you see the input coming in. The hidden layers is where a lot of the computation now happens, right? And each layer here is a typical node, right? So each layer has these neurons or nodes, and each node has the weights and the biases, which are the parameters of the neural network. And like we saw before, the input comes in from here. You've got the input from here and the input from here, right? You've got these 3 inputs coming in. You'd first aggregate it. You pass it through the activation function, and then you'd pass the output of that to the next layer. That would happen to each neuron here. Now, typically, each layer uses the same kind of activation function, okay? So if this layer uses a ReLU, then every node here will use the ReLU. The next layer could be something else. You could have a different kind of activation function depending on the problem, but all the nodes in that layer would typically use the same activation function. Okay. So you started understanding the basic idea of an artificial neural network, and I'm going to use the ANN instead of artificial neural network in some of the future slides. So you can see, it's effectively a big function, right? If you're familiar with what a function is, it takes in an input, it returns an output. And there's a lot of calculation happening in between. It just happens that the calculations here are basically these tiny functions that are connected to it. Great. So what do you do if you have such a neural network and you have to predict something? So the output is called yi for a given input or a given case I, right? And so what happens is you first taken the raw data. Now, typically, you would have to do some pre-processing on it. So, for example, so neural network takes in numbers, right? It takes in numbers. So, if it's a number data set, numerical data set, ideally you non-dimensionalize it. You try and make sure that the inputs are between 0 and 1, something like that. If it's text, you vectorize it. So you would again get a set of numbers. If it's an image, you use the pixel values, and again you might scale that. So that pre-processing generally happens. Now, from now on, we'll just focus on the network, but assume that depending on your data type, there is some form of pre-processing, and then you get these input data sets xi. The x's come in, pass through the network in a forward direction, and so it's called a forward pass, right? Because all the information is moving forward. And at the end of it, you get the output y hat I. Right? Now, why are we calling it y hat I? Because when you train, you'd have training data, and we'd call that the actual output, the ideal or the real answer that a network should have, y I, where I denotes which data sample or which input it is. Okay. So once you get your output, you might, in some cases, depending on the type of input you have, post-process it. Now, each of these neurons has its own weight and bias, right? And so the quality of the prediction or the output you get, as you can imagine, is determined by the weights and the biases, right? And if you remember the example we just looked at, I just set those values of those weights and biases, right? Now, if you just set those values and pass the input, you get an output, but it's not necessarily going to be the right output, right? It's not going to be what you want it to be. So if you have a neural network that's trying to look for pedestrians, right? And it's the neural network that's powering a self-driving car. If I just tell you, oh, these are the weights I'm going to put in, well, it's not necessarily going to predict any pedestrians, right? It's probably going to be absolute junk. So you need to set the weights of the neural network, which are the parameters, and the biases. And that process of finding these weights is called the process of training a neural network. Now, what is the first thing you need to do to train it? You need to have what you're training it on. So depending on the problem, and I've just used text data, but if it's numerical data, but if it's you're building a version of ChatGPT, you're going to need a lot of text. If you're building a self-driving car model, then you're going to have to figure out the images, right? And it's going to be images with cars on the road, without cars, pedestrians, and so on. So you're going to figure out your data. You're going to clean it. So you're going to take out data sources. So for example, in this case, if you have a row here with columns that have junk values or that are empty, you're going to have to filter them out. And then what you're going to do is you're going to break it into a training set and a test set. And I mentioned this briefly as well. And as we do actual building, you'll really start seeing the importance of this. Now, the reason we do it is if we take all our data and we train on that, we'll get a model that's exceptionally well trained on this data. And we're going to train it and we're going to measure the accuracy of the model. And it's going to be, if your model is good enough, it's going to be very good. You're going to say, wow, my model is brilliant. It predicts with an accuracy of 98%. The problem is it predicts accurately on this data. But now if you put it in a real world scenario and the data that it sees is a different value, it might actually be very wrong because it might be extremely biased by this data. So what ends up happening is by breaking the data down into a training set and a test set, the data is not trained on this test set, which means it hasn't seen this data. And typically, if the data coming in is very ordered in a sensible way, you might actually randomize it first, right? You might change the order or shuffle it like you do with a deck of cards, so that the training set covers a lot of different, data points from the data set. But once it's trained on the training set and you have an accuracy that you think is good enough, you'd go and evaluate it on the test set. And generally, the accuracy on the test set will be lower. And so if you feel that you need the model to be, say, 95% accurate, expecting 100% accuracy is unrealistic. So if you say it's 95% accurate, if on the training set it's hit 95, chances are in the test set it will be 90% or 80%, right? Depending on how well your training data has been selected. So you're probably going to have to go back and train again and reduce this accuracy further till it hits the required amount of accuracy on the test set. So this idea of training on too much data is called, where now your model does brilliantly well on that data set, but then is very poorly performs poorly on data it hasn't seen, is called overfitting, right? And this is a machine learning term. So any machine learning model that will, including some of the videos, some of the lectures or sessions we look at on regression and so on, you'll see the same phenomenon. So now, once you've got your training set, what you do is you break it down into the inputs to the model and the output of the label, which is the truth, right? So for this input, the model should return this value ideally. And so that's the ideal output. And this is the Y, right? And that's why we've used a Y hat in the previous lecture when in the previous slide when looking at the output of the deep learning model, because the Ys are the actual truth or the actual labels of the data. Okay, so we've figured out how to get the data. The next thing you need to do is select the architecture of the deep learning model. So what you're going to have to figure out is how many layers do you want, what the activation functions in each layer are going to be, right? And so once you figure that out, you've got your data and you've got the layers, you need to initialize the model, because initially you have your data. You need to first, to get an estimate of how good your model is, you need to first pass your data through it and get an output, right? So to do that, you need an initial value of the weights and the biases of the neurons. So what you do there is you can either initialize it with random weights. You could say set everything to say 0.5. Bad idea in general, but you could do that. You could initialize it randomly, which is something that's quite commonly done. Or if you're actually aware of previously trained model that is exactly of the same architecture, so has the same nodes and the same activation functions, you could use that, right? You could use that model and get started, and then you fine tune your model, right? So the word fine tuning comes from there, where you already have a set of weights and then you're refining it even. Now, typically, because you have a number of layers, you see nomenclature like this, where each layer you indicate it with, this upper I, and so that indicates it's the weight for layer I, and then J indicates which node it is. So W11 would be node 1, layer 1, and so. Now, this will become more relevant when we actually start, building the neural network in the subsequent sessions. But just to introduce you to the nomenclature. So, okay, we've got the data, we've got the neural network. What we are going to do is we are going to start here. We're going to take the first data point and we're going to pass it through the neural network. Now, one point I forgot to mention when I introduced it there, but this neural network is called a deep learning model. And the reason it's called a deep learning model is because it's got more than one layer, right? Apart from the input and the output, it has another layer. And so it's called a deep learning model, right? So if it's just the input and the output, then it wouldn't be called a deep learning model. But it's got multiple hidden layers, and so it's called a deep learning model. So now the data comes in, passed forward. So it's the forward pass, right? Now, once you've passed it in and you've got an output, you need to know how good your model is, right? So how do you do that? You need to find the loss or predict the loss or the error. So that's where the loss function comes in. So the loss function, which is connected to this, is a way to predict the error in the model. What it does is it takes the actual label or the actual truth and it takes in the prediction. And it tries and finds, and I've just used yi minus yi bar, which is just symbolic, right? It basically comes up with a metric. So this is a more realistic example of a loss function where it's the mean square error. It finds a way to measure the error in the prediction. And the error in the prediction is not just done for one point, but it's done for the data set, right? So you sum up these errors, because that will tell you the error in the model, because it could be very good for one point and very bad for another. You need to understand the big picture. So now you've put the data in, you've put multiple data points in, and you've got the loss. Now what do you do? Well, the goal is to minimize the loss, right? You want to reduce the loss as much as possible because that means your model is extremely accurate. And how are you going to do that? Well, you're going to change or set the weights of this neural network. So one way to do it, very nice. You go in, you say, okay, this I've got the weight here. The value here is 0.5. I'm going to make it 0.7, and I'm going to see what happens to the loss. Then I'm going to change the weight here. The weight is 0.9. I'm going to make it 0.8, and you see what happens to the loss, right? So that's one way to do it. Now, as you can see, it's already with a network like this with 3 layers and a few nodes or neurons. It's already quite complicated. It's not going to be easy to do it. And we also, for big systems, we want to code this up, right? So you need a better way to handle this. So luckily, we get what is called backpropagation. So what is done is the loss function is available. Now, backpropagation is a complex topic. So we'll have a full lecture on it. I'll just give you the basic idea. Once you get the value of the loss, what you can do is compute the sensitivity of the different parameters of the network with respect to the loss. And what I mean by sensitivity is if I change the loss by 1 unit, how much does the loss function change? If I change the weight here by 1 unit, how much does the loss function change? So that's the sensitivity of the loss function to this weight, and so on. Now, what is done is once the loss is computed, you first compute the sensitivity of the loss to the value here. Then you keep moving that further and further back. So it's called a backward pass, where the sensitivity of the loss to the output, then you have the sensitivity of the output to the weights in this node. Then you have the sensitivity of the weight of the value or the out of this node to these two nodes, and so on. So the sensitivities are passed backwards using what is called chain rule, right, in differentiation. And you can compute the sensitivities of every weight in this system to or the sensitivity of the loss function to the weights or the parameters of the system. Okay. Now, don't worry about it. It might sound a bit complicated, but we'll cover this properly in one full session where you'll actually go through this and actually compute them by hand, and then you'll code it up. But what we've ended up with is we've got the loss, and we now know the sensitivity or the change or the sensitivity of the loss function with respect to the parameters. So now we know that if I change this by 1, the loss will change by this. If I change this by 1, the loss will go up, and so on. What you do next is you update the losses, right? Now, is there a smart way to do this? There is, right? Luckily for us, researchers have done a lot of work for us. So you have what is called an optimization process. So optimization consists of algorithms that take in what is called an objective function, which in this case is the loss function. So objective is the function that you want to optimize. Typically, you want to minimize or maximize that value. You have the variables, which are the parameters that the optimizer works with, and the optimizer changes to measure the objective or the loss, right? And so you pass and if you have the sensitivities, right, here, which we have got from backpropagation, then you can use an approach called a gradient-based optimization. And with a gradient-based optimization, what you can do is you can take in these sensitivities, you've got the initial guesses of these weights and biases, and the optimizer, using these gradients, finds the best possible change or direction to make these changes in these weights to minimize this loss function. And so as we actually do our next set of cases in the next few sessions, you'll actually see how the optimizer actually works in this scenario. But effectively now we've completed the loop. You've got the initial weights, you compute the loss, you do a backpropagation, and you get the sensitivity of the loss function to each of these weights. You pass that to an optimizer, and the optimizer uses these sensitivities to change these weights to try and reduce the loss. And this cycle now continues again and again till the loss function is what we want it to be, right? So it hits a certain level of accuracy that we want it. So hopefully that makes a lot of sense, right? Okay, excellent. So we've covered what the basic idea of a neural network is. We've looked at what the parameters are. So the parameters are the internal parameters, which is the weights and the biases of the neural network. And this is what the training process teaches the network. You'll also hear the term hyperparameters. Now, the hyperparameters are the big picture parameters of the neural network. So it's the number of layers, the types of the layers, And then as you get into optimization, it's the learning rate and the momentum of the optimization. Now, don't worry about them now. We'll cover them as we do optimization. But it's basically how the gradient-based optimizer updates the weights, right? Then you have the number of epochs. Now, one epoch is when all the data in the training set has gone through the learning model, right? So that becomes one epoch. Now, ideally, you want to pass the data through it multiple times or have multiple epochs. And as you do that, the model learns better. And then you have a batch size. So now when we did this example, we said, I'm going to pass the data in one at a time. Actually, for efficiency, you don't do that. You actually pass it in what is called a batch. So it's a collection of inputs that gets passed into the network in one shot. And the network computes all of those values at a time and returns all those values, all the output for all those values. And that's kind of what a batch is. So training is typically done in batches. So one of the reasons why deep learning models is so popular is because deep learning models function very well as you increase data set size. So now if you employ a traditional machine learning model, what you see is initially it will do really well. Then as you increase the size of the data set, the traditional machine learning model stagnates, right? So you can't increase the accuracy a lot. However, with a deep learning model, as you increase the size of the model, which basically means you're increasing the number of parameters, right? So you're using different layers with different activation functions. But what you're doing is you're increasing the size of the model. You're increasing the number of neurons and so the number of parameters. And as you do that, you see that these models perform a lot better. So this has got a smaller number of neurons, but as you increase it, it gets a lot better. So a good example is with the GPT series, right? So that powered Chat GPT. You're at GPT-4 now, GPT-4o in fact. But GPT-1 was a lot smaller, right? It was a much smaller sub-billion parameter neural network. I believe it had around 117 or something million parameters. As they increase the number of parameters, and GPT-4 now has more than 1 trillion parameters, the model is doing outstandingly well, right? So it's a clear example of how, as you increase the parameters of the model, you can train on more data and the model gets better. Okay, so a quick look at the advantages. We already discussed one, which is the ability to handle scale. Another advantage of a deep learning model is with the same basic principle, of a neural network, you can handle a number of different types of data. And you can handle unstructured data. So you can handle images, you can handle audio, you can handle text, right? The nodes of the neurons would be different. The pre-processing and the post-processing will be different. But effectively, with a similar architecture, as long as you can convert these into numbers and you know the right kind of neural network to build, you can use the basic principle of deep learning to build complex models. So, ChatGPT, DALI, all these different models are built on deep learning, right? Okay. Another advantage of deep learning is because of the fact that it's got these number of functions connected in very complicated ways, and activation functions are typically nonlinear, you can actually capture intricate or complex patterns, right? And you don't need to worry about how you're capturing it. You don't need to. So typically with machine learning, you have to build what are called feature spaces or features, right? You have to figure out what features you want to capture and build accordingly. In this case, the neural network takes care of that. Right? And they're very flexible as well because you can try out a neural network, and if it doesn't work, you can play around with the hyperparameters. You can increase the number of layers. You can change the different neurons and activation functions, and you can get performance. So that makes deep learning extremely useful. Now, there are a number of different architectures depending on the problem you're looking at. So I'm just giving you a list of some of the architectures that you'll probably see or hear of. You have multi-layer perceptrons, which is kind of what we looked at. It's a really clear example of that. But there are also convolutional neural networks, which is what is used for images. You have recurrent neural networks, which is used for time series data. You have models like transformers, which is now what pretty much all the large language models are powered on. You have generative adversarial networks, which are great at generation. You have autoencoders. So there are a lot of different deep learning architectures. Now, at this point, I feel it makes little sense to really go through all of this in detail. As we do the series, you'll start seeing examples, in the later videos and in other series as we keep building, right, on these different architectures. So in this video, just to give you a quick summary, we've looked at the basic idea of a neural network. Just to summarize, you can recap in your head. We've looked at what a node is or a neuron is. We've covered what an activation function is. Then we've looked at the layers, right, and how these neurons are arranged in the form of layers. We've looked at a forward pass where the data is passed in and you get an output. Looked at how you compute the error when you're doing training with a loss function, and how you compute the sensitivity of the different parameters, right, with a backward pass and backpropagation. We'll cover a lot of this, most of these, topics in a lot of detail as we start building. Right? I think the best way to learn is practically, but you've hopefully got the big picture of what these terms are. We've understood what role an optimization model plays in this, right? And we've kind of talked about gradient-based optimization. You also understand the difference between parameters and hyperparameters. And we've looked at some of the advantages. So we've put a small quiz on this lecture so you can cement your knowledge a little more, and that's at pixagon.ai, and you can go to lectures and go to basics of deep learning, and you'll see that quiz there and the lecture notes. And in the next lecture, we'll now start getting hands-on and start coding up a first learning model. Now, it's not a deep learning model because I think you need to first understand what a neuron is, right? And build a simpler model first, and then we can go and build more complex models. But it does qualify, I think, as an AI, right? Because it is a model that is trained and learns to do something. So stay tuned for that. Hopefully you've enjoyed this lecture. See you soon.